All right, so this is the first of two lessons that finish off chapter 4, in which we look at solving trigonometric equations. Now, this is something that each of the 3 chapters in trigonometry returns to at the end of the chapter. Clearly, this is something that is sort of a glue that connects all these different chapters together in trigonometry, so it's pretty important. And I split this first lesson up into a couple of different parts. First, let me just remind you of 2 different ways of describing an interval. And so, here's a...
Hi, Dennis. Could you check with Mr. Breen in the office? Dennis, please check with Mr. Breen in the office. Thank you.
Okay. Hope you got that. So, first, everything you see, if we see this and this, they mean the same thing. The one left we call set notation, the one on the right we call interval notation. I don't really care what it's called. I care that we know how to read it. You learned this in grade 10. You may have not seen it since grade 10. But they both mean everything from 0 up to 2 pi, not including 0, but including 2 pi. So the main difference with interval notation is you can't tell what variable it is. With set notation, the variable is explicitly stated. But you can essentially show all the same things either way. So on the left, this here means all values greater than 0 for theta. Well, in interval notation, we don't show the variable, but we don't include 0, so we have a round bracket, 0, and we go up forever, so we put infinity. And we have another round bracket because you can never reach infinity. A square bracket means you include that value, but remember, infinity is not a number. Next, all real numbers. For this, well, how do you show all real numbers? I go from negative infinity to positive infinity with round brackets for both. And then the other way around, I have something in interval notation I want to put in set notation. So for this, pick any variable I want. I don't know, I'll go with x, I'll be boring. So we go from negative 180, including negative 180, up to positive 180, but not including that. So negative 180 degrees is less than or equal to x, or any variable you want, which is less than 180. And those two are equivalent. So hopefully that all sounds familiar. Most likely you've been using set notation far more in the last year and a bit. Interval notation is part of Math 10, but it's not a big part, and quite often it's not used again until now. That's it. The purpose of that is that to remind you what something like this means. But I want to solve this equation. And you did this sort of stuff in pre-calc 11, not with radians, and the equations weren't as complex, but hopefully you were introduced to this idea in pre-calc 11, because that makes this a lot easier. Again, this is one of the fundamental underlying themes of this trigonometry unit, how to solve a trigonometric equation. And none of these will require a calculator, so I'm not going to use a calculator for any of these. So I want to solve where minus 2 sine of theta equals root 3, with a restriction where theta can be any value between 0 and 2 pi, not including 2 pi, but including 0. What does this mean? In terms of rotation, this means 1 full forwards revolution. Right? What I just sketched out as a rotation, that's what's being described right here. The first forwards positive revolution. This is the most common restriction to put on an equation like this, if we're thinking in radians. Just 1 full forwards revolution, because I will say, if there is no restriction, there's going to be an infinite number of answers to this, which we'll talk about. But if I don't want an infinite number of answers, I need to have some sort of restriction. That's it. How do I solve this? First, let's solve for the trigonometric function. So let's divide both sides by negative 2. And so I get the sine of theta equals negative root 3 over 2. It doesn't matter if the negative is in the numerator or the denominator. So next, first, hopefully root 3 over 2 looks familiar. But even before then, I need to think about, OK, I'm trying to find theta. And I now know the sine of theta is going to be a negative value. So let's think about, I can now know what quadrants that must be in. So let me kind of visualize this. So where is sine negative? Sine is negative in the 3rd quadrant and the 4th quadrant. And I know that from my cast rule, because I know that sine is positive in the first 2 quadrants. So I know my solutions are going to be in the 3rd and 4th quadrants. And now I can visualize my 2 solutions. I know one of my solutions must look like this. One of my solutions must look like this. And that must be it. Because again, I'm only looking from 0 to 2 pi. So I'm not looking at any backwards angles. I'm not going around more than once. So all that's left now is what's my reference angle. If I can figure out my reference angle, if I can figure out what goes here and here, I know it must be the same thing. Then I can piece this all together. To figure out my reference angle, I need to look at just the root 3 over 2. Okay, at this point, the negative doesn't matter to me anymore. The negative told me the quadrants it's in. So now I need to think to myself, the sine of what angle equals root 3 over 2? That's what I need to think to myself. The sine of what? And ideally from memory, we know that that angle is going to be 60 degrees. Or even better in radians, it's going to be pi over 3. And that angle is my reference angle. So what I just did relies on us having memorized those special angles from the last section. And ideally, we can get from here to here in a few seconds. If it takes us much longer than that, if we have to start drawing out triangles, again, we're getting bogged down to very early stages of this section. And so that means I know not my answer is pi over 3. I know my reference angle is pi over 3. So now I can go back to this. I know each of these is 60 degrees, or pi over 3. But I'm going to try to stick with radians. So now I got everything I need. So now I can state my answers. I can say, therefore, theta equals, the angle I drew in red, I know is going to be pi plus pi over 3. All of that together. Pi being this part right here, pi over 3 being the reference angle. So I know that part in red is going to be pi plus pi over 3, which is 4 pi over 3. So let me give myself a bit more space here. Okay. And what's my angle? My answer in green? Well, the angle in green, I can think of it as one full rotation, take minus pi over 3. So I can think of it as 2 pi minus pi over 3. And there's other ways of thinking about it, but that's how I'm going to choose to think about it. One full rotation, but then take away 60 degrees. Take away pi over 3 radians, which is 5 pi over 3. And so that's my answer. Now keep in mind, if there was no restriction, these would still be part of my answer, but there'd be infinitely more on either side. If my restriction was different, if it was 0 to 4 pi, then I'd have these two answers plus 2 more. What if I go around again, 1 more full time? So lots of possibilities. That restriction is quite important, but in this case, I'm done this question. 2 answers. Okay, the next question is the exact same, but there's no restriction. So if there's no restriction, it literally means what I just said. There's no restriction. I mean, there's nothing stopping you for x, or theta in this case. So this means theta can belong to the all real numbers. We call this a general solution. And a question like this either has no solutions or infinitely many solutions. Well, I've already done all the work for this, essentially. So I'm not going to I mean, it's the exact same equation. So pretty quickly, I get to the sine of theta equals negative root 3 over 2. And I've already found 2 of my solutions. I already know that one of my solutions was 4 pi over 3. That's my first positive solution. I know my next positive solution was 5 pi over 3. But it goes on. So how do I find more? Well, keep in mind, after this, if I want to find an angle less, I just got to subtract 2 pi from any of these. Right, if I go minus 2 pi, I'm going to get an angle that's coterminal with 4 pi over 3. Or if I add 2 pi to this, I'm going to find another angle that's coterminal with this. And I can do the same thing with 5 pi over 3. If I subtract 2 pi or if I add 2 pi, I'm going to find all my other answers. So I could start to list these out. For example, if I add 2 pi, actually no, I'm not even going to do it. I already know these just kind of go on forever in either way. And so the key is, if I know 2 of my solutions in one full rotation, I know all my solutions because I know they're all going to be coterminal with 4 pi over 3 and 5 pi over 3. So how do I express this? How do I express what I just said algebraically? Well, I say the general solution is at 4 pi over 3 for one of them, plus any multiple of 2 pi. And I think it was our very first lesson in trigonometry, we saw answers like this where we're expressing all angles that were coterminal. And there's also 5 pi over 3 plus any multiple of 2 pi. Sorry, I forgot about the n right here. Any multiple of 2 pi. And then I really should state where n belongs to the integers. Because that's the whole idea right here, that n can be any number we want as long as it's an integer. Integers being whole values that are positive or negative. So essentially that allows me to just add any multiple of 2 pi or subtract any multiple of 2 pi to any of these answers. And that's the general solution. So notice, if you compare this to what I did up here, removing the restriction doesn't inherently make it harder, but your answer will always be some sort of expression like this with, some repeating value. All right, so Let's look at this, different equation now. Let's solve this. So like before, I first want to isolate the trigonometric function. So I'm going to subtract 2 from both sides and divide by 2. And pretty quickly I get the cosine of theta equals -1. Okay, hope that sounds familiar. -1 is one of our angles that's between quadrants. It's sort of a quadrant angle, we can call it. So where was that again? Where did cosine equal -1? Let's think. Let me draw this out. If I think about the cast rule, okay, cosine is negative in these quadrants. But it's not going to be in these individual quadrants. So I know it's not going to be quite like this, because cosine is -1 right between two quadrants. Sine and cosine equals 0 or 1 or -1, always at the borders between different quadrants. And that was actually, I think, a final problem from, I believe, the very last lesson. So where is it? Well, one thing I could do is realize it must be right here if it's between those two negative quadrants. Or even better, we want to memorize where cosine is at what the value of cosine is at these sort of border angles between quadrants. And we want to really memorize that cosine is 1 at 0. Cosine goes down to 0 at 90 degrees. It keeps going down to -1 at 180, goes back up to 0 at 270, and then around and around and around. And for cosine, we really just want to memorize that cosine starts at 1. If we think about 0 being the start, which is pretty common, starts at 1, goes down to 0, down to -1, back up to 0, around and around and around and around and around. And so once I know that, I know the angle I'm looking for is from here to here. Or I should say, that's one of my angles I'm looking for, because again, there's no restriction on this. So I'll start with that. I'll say theta equals, that's 180 degrees, but in radians, that's pi. Okay, so that's it. I know there's more. I know there's infinitely more. So where's the next one? Well, I got to go another full rotation to get there. So I got to add another 2 pi. And I can do that as much as I want. If I add 2 pi once, I get 3 pi. Do it again, I get 5 pi, and so on. Plus, I could also subtract 2 pi. I could go less than it. So I can now see my list. So how do I express my answer? Say theta equals pi plus any multiple of 2 pi, where n belongs to the integers. And so in the end, like everything we've done in this chapter so far, not a lot of algebraic work, but a lot of connections to make. And anytime you see sine or cosine equaling a value like 1 or 0 or -1, hopefully we know it's always going to be, those are really kind of key numbers, and they are between quadrants. They're the borders between quadrants. Notice right here, this is not in quadrant 2 or quadrant 3. It's the border in between them. And once we recognize that, we should be able to figure it out pretty quickly. And again, for sine, you want to memorize that sine starts at 0, goes up to 1, goes back down to 0, goes down to -1, and then around and around and around and around. If you can memorize this and this, which we can, then that'll not only make this a lot faster, it'll really help us out a lot going forwards in this big unit on trigonometry. All right, let's look at this one. So this time I have a different equation and I have a restriction. So first of all, let's think what this restriction means. Between 0, including 0, and pi. That represents, in terms of rotation, that represents just the first forwards positive rotation. That's what's being described there. From 0, including 0, up to pi, but not quite up to pi, but not including pi. So that restriction is what I've kind of sketched out there. That's all we're looking at. Okay, so I'll put that on hold. Let's solve for cosine first. If I subtract 1 and divide by √3, I get the cosine of theta equals -1 over √3. Okay, next. Where's cosine negative? Write that negative there. We'll think about my cast rule. Cosine is negative in the second and third quadrants. Okay, well, going back to my restriction, I know I'm only paying attention to this part right here. So I know my answer is going to have only one solution. So now I know my answer has just one solution. So unlike all my previous ones that had at least 2, if not an infinitely many, this equation here will have just one solution. And it's all because of that restriction. It's really just the part I've highlighted in yellow. What is that angle? OK, at this point, I don't need the negative anymore. I need to pay attention to the 1 over √3. I need to think to myself, the cosine of what angle equals 1 over √3? Well, we think back to memory, and 1 over √3 should sound familiar, but not for cosine. tangent of 30 degrees, or the tangent of pi over 6 is 1 over root 3, but not for cosine. None of the special angles have a cosine equals 1 over root 3. So this means this is not a special angle, which means we need a calculator. Now, you may think, hey, didn't the teacher say we're not using a calculator on this first part of the unit? But yes, for assessments, for your homework quiz and your test, yes. But after this chapter, we're to be using a calculator. And honestly, questions like this are actually harder. So the worst thing you can do is skip these because, oh, he's not going to ask me on a test. There's ways I can ask this. And this is actually going to be harder. Your life is easier when we're dealing with special angles. So whatever that reference angle is from here to here, it's not 30, 45, or 60. So what is it? Well, now I need a calculator. How do I use my calculator? I need to go to my calculator, and I want to use the inverse of cosine. Right? I know the output of cosine. I don't know the input. Well, if I use the inverse of cosine, those inputs and outputs are reversed. So if I go inverse of cos of 1 over root 3, notice I'm not putting the negative in. I think that negative will just confuse me. The negative was only important for knowing my quadrants. I know the quadrant it's in. I know everything. I know there's one solution. I just don't know the reference angle. And so if I put the negative into my inverse cosine function, it's probably going to give us information that is not wrong, but is going to be extra confusing. And again, once we know the negative tells us the quadrant, I don't really need to worry about that negative anymore. So just where does cosine equal 1 over root 3? And if you go to your calculator in radian mode, which I recommend keeping it all in radian mode, it will tell you about 0.955. Okay, so that is my reference angle in radians. If my calculator was in degree mode, it would give me the equivalent number in degrees. So now I know my reference angle. It's not as pleasant. I'd much rather have something in terms of pi divided by 3, pi divided by 6 than this. And that's just, that's just 0.955 radians approximately. It's not pi times 0.955. It's just approximately 0.955. And so what's my answer? Well, my one answer, I now know is going to be, if I look right here, my reference angle, I now know is about 0.955. So I can figure out this angle by going pi and then take away 0.955. And so that's my only answer. And so I can say theta equals pi minus 0.955. Or I can put a dot over my equal sign because I know this is an approximation. At this point, if I go to my calculator, I mean, it's not wrong. I'll do it. But I get this, approximately 2.19. Is that really better than what I had before? If you think so, sure. I don't think so. I don't think it's worse. They're both approximations. I kind of like the first one better because I see how we figured out this value. It was pi radians take away the reference angle. They're both approximations, so neither's actually better than the other. I'm happy with both. And notice again, there's a very good chance you found what I just did harder than some of the previous ones because the reference angle is harder to visualize. If I ask you to visualize pi over 6 radians, I bet you can visualize that fairly quickly. Can you visualize 0.955 radians very well? It's yes, but it's going to be harder. You have to first think about what 1 full radian was, which was about 57 degrees. And it's a tiny bit less. So you can visualize it, but it's going to be less familiar. OK, let's try this one. No restriction. OK, so I want, there's no restriction. Again, I'm going to have an infinite number of answers or no answers. So let's divide by 4. I get secant of theta equals 5/4. OK, so now it's secant. I'd rather deal with one of the primary trigonometric functions. And all I have to remember is, OK, secant is the reciprocal of cosine. So I can change this to cosine theta if I just find the reciprocal of 5/4. There we go. So dealing with secant or cosecant or cotangent, most of the time you just want to fairly quickly bring it back to one of the primary trigonometric ratios. As long as you remember which ones are reciprocals of which, it's pretty easy to deal with. So now I'm just going to deal with cosine. Now 4/5, again, I never asked you to memorize where cosine equals 4/5. So again, we'll need a calculator. Because my reference angle is not a special angle. OK, so like before, I go to my calculator and I go find the inverse cos of 4/5. And again, notice, now that we've learned about inverses, for cosine or any trigonometric function, you insert an angle and you get out a ratio. For inverses, you insert a ratio and you get out an angle, right? So ideally, our work on inverses make this feature on our calculator a little less mysterious, what it's doing. If you're in radian mode, it'll give you an answer in radians. If you're in degrees, it'll give you degrees. I'm going to stick with radians. I get about 0.64. And again, so that is my reference angle. Again, harder to visualize. Okay, it's about 64% of 1 radian, but as long as I have the number, I'm okay. So now let's use this. I don't actually have a lot of work left. There's no restriction, so now let's think about, okay, where's cosine positive? And I could have done this earlier. Because again, I also could think about where secant is positive, but instead of me thinking about where secant is positive, let me think about where cosine is positive. Same places. So where is cosine positive? Cosine is positive in the first quadrant and the fourth quadrant. And so now I know my reference angle. This and this I now know is about 0.64. Okay, that's really important because now there's not much left. So how do I state my general solution? Well, to find my general solution, if I go back a few questions, let's get back to, where was it? My first one, here. For this one, the main idea is first I need to find all my solutions in one rotation, and then I generalize it. So let's do the same thing here. Let's not worry about the general solution yet. Let's find my two, I'm going to generally find my two first positive solutions. Well, they don't have to. I'll mention another way of looking at it. So I'm going to find this solution here, and I'm going to find this solution here, and then I'll generalize that. So, for example, my first one that I've drawn in red, that one in red is literally the same as the reference angle. So 0.64. Anytime you have an angle between 0 in the first quadrant, that's between 0 and 90 degrees, or 0 and pi over 2, your reference angle is also the angle. There, okay, so now in green. How do I find the one in green? It's almost all the way around, so it's going to be 2 pi minus the reference angle. Which is about 5.64. So 0.64 and 5.64 approximately. And now for each of these, I can then, once I got these two basic ones, I can add or subtract any multiple of 2 pi to find any other angle coterminal with it. So each of these I'm going to say plus any multiple of 2 pi. Plus any multiple of 2 pi. And I'm done. However, I will mention another answer a little bit better, but it's not necessarily better, but I just said I kind of like it better. So while this is great, if I look back here, again, to find my general solution, I don't have to pick the first two positive. That's one common way of doing it. I just need to pick all my solutions in a single rotation. So another way I maybe like better is to keep that one I've shown in red, but also think about this one going backwards. Think of my first forwards at my first negative angle. They still, they still don't overlap, so they're still different rotations. And they're kind of pleasant actually if I do this, because in this case I would get theta equals, I can either say they're positive 0.64 radians or minus 0.64 radians. So I can summarize it all like this, as plus 0.64 plus any multiple of 2 pi n. And so this here and what I have down here are exactly equivalent. I kind of like the first one better. But notice, this plus or minus 0.64 covers this and this angle. And then from that, once I have that, I can add 2 pi into as much of it as I want. Whereas these two here cover the same two angles, or they're coterminal. They're I think a little bit messier. That's it. There's no way around it. There's lots of ways of approaching this. And so we want to try to understand all of these. I'm sure you can start to realize why we need some time for this. And before I kind of finish this off, just keep in mind the questions that do involve a calculator. Use a calculator, but you shouldn't have too many of them. What you really want to avoid, there's the bell. What you really want to avoid is using a calculator on angles that involve a special angle. For example, let's say at some point you want to figure out where the cosine of theta equals √3/2. If we're using a calculator for that, we're setting ourselves up really, really badly. For not just the next test, the whole unit. There's some things we just need to internalize. And so, for this, you want to know that is 30 degrees, or that's pi over 6. You want to memorize that. If you're using a calculator for those special angles, that will be a problem going forwards. And so I hope you just trust me on that, because I want to make this challenging unit as doable as possible. We don't want to make it harder on ourselves. But now I'm done talking. So